Then I will start. We'll start the invited lecture. So welcome everybody to the June 3, 2 p.m. invited lecture by Professor Zoe Shipton from the University of Strathclyde. Professor Zoe Shipton will talk about pore-scale capillary heterogeneity in reservoir and its influence on reservoir-scale flow. I'm the moderator. I'm from Sorbonne University. And I will introduce Professor Shipton. She is affiliated to the Department of Civil and Environmental Engineering at the University of Strathclyde. She received a PhD from Edinburgh University in 1999. After that, she moved to a number of places, including Utah and Dublin. And she has produced over 100 works referenced in ORCID. Her major interests are growth and development of faults and damage zones, fluid flow in fault zones, such as hydrocarbons, CO2, geothermal fluids, and flow out of radioactive waste sites. And without further delay, I now give you Professor Zoe Shipton.
Thank you very much. I will just share my screen if you give me a couple of seconds. So yes, thank you very much for inviting me to talk at InterPore this afternoon. I'm primarily going to present the results of the PhD work of Carla Romano, who is now at the University of Wisconsin-Madison. So I'd like to start out by thanking Carla and my co-authors. I also want to start out by kind of telling you why this matters. I know InterPore is a fantastically interdisciplinary conference, and I'm going to be talking about some fairly small-scale structures in geological reservoir rocks, but I wanted to start off by telling you why you should care if you weren't a geologist. So this is a graphic produced by the Geological Society of London, outlining all of the ways that geoscience can make a contribution to the UN Sustainable Development Goals, in particular thinking around net zero. And if we are to reach net zero, the IEA has created a number of scenarios or pathways for how we can reach net zero by 2050. And there are 5 key technologies that are going to use the subsurface, the geological aspect, geological engineering technologies that are going to help us meet net zero. So the first, counterintuitively, is hydrocarbons. So we currently produce 91 million barrels a day in 2020. The IEA net zero forecast has us still producing 24 million barrels a day by 2050. And partly that is because we will still need certain aspects of fossil fuels, but mainly because we will need petrochemicals for creating plastics and drugs and shampoo and things. So even by 2050, we'll still be producing hydrocarbons, but those may be from harder to reach types of geological formation. To offset the CO2 produced by the combustion of hydrocarbons, but also from other industries such as cement production, by 2050, we will need to have captured 7,600 megatons of CO2. By 2020, we're only up to 4 megatons. So we need to see an enormous increase in the amount of carbon capture and geological storage projects, which requires a real understanding of how that CO2 might go back under the ground. Linked to both of these is hydrogen. And again, the IEA forecasts have 30% of hydrogen coming from fossil fuel-based sources with CCS by 2050. So the hydrogen economy will replace some of those fuels, and particularly for transport and possibly heating. But again, really relies, a third of that hydrogen relies on geological sources. When we think about geothermal energy, only 2% of our buildings at the moment are heated by renewable thermal energy. By 2050, the IEA would like to have that up to 12%, and 2% in industrial buildings are currently at 0%. So again, we need to see a big ramping up of the extraction of heat from rocks. Energy storage is going to be required to balance the grid with intermittent renewables such as wind and solar. And there is a suite of subsurface energy storage options, so compressed air energy storage, hydrogen, other fluids, And the idea there is that you would have either a cavern or a porous media that you're injecting fluids in at times of excess electricity production. And then when you have higher demand, you recover those fluids and use those to generate more electricity in some form or another. So subsurface energy storage is likely to be particularly valuable, according to the IEA, for longer duration or seasonal storage. So taking the high volume of electricity generated by solar in the summer and being able to recover that in the winter or so on. And finally, nuclear power is estimated to double by 2050. I couldn't find the data on this globally, but within the UK, the radioactive waste management have estimated that if all the new build nuclear power stations go ahead, then by 2050, the UK will have 750,000 cubic meters of radioactive waste, 10% of which is due to these new builds from 2020 to 2050. So although a lot of that waste has already been produced, we still require a solution for that waste to keep it away from the surface, keep it away from people, and keep it away for a very long time, 100,000 years or so. So we require to understand the subsurface. So all of these technologies mean that we need a really significant understanding of rock mass heterogeneity. We need to understand how those heterogeneities control the flow of a variety of different fluids. So for geothermal, we're talking warm water, or if we're thinking about geothermal cooling, we cool water, putting that back in, and the interaction of the cool water with the rocks. We want to think about brines, we want to think about gases, whether that's gas in a hydrocarbon reservoir or gases released by radioactive waste. And we want to think about the disposal or mobilization of contaminants. And we need to understand this so that we can reduce the risk of any contaminants moving within the subsurface to receptors, whether that's shallower drinking water aquifers or to the surface. And we want to understand the risk of seismicity that might be generated by any of these technologies. And I want to emphasize that in the past, with hydrocarbons, we've got really good at taking stuff out of rocks, so producing things. And that's what I've put here in blue, are the technologies that rely on producing fluids out of rocks. What we're now moving towards is injection. So CCS, carbon capture and storage, relies on injecting material into rocks. And nuclear waste doesn't really rely on injection so much, but it relies on containment. But things like longer duration energy storage, or even thermal heating and cooling systems, require an understanding of cycling, of cycles of injection and production, which introduces the concept that we might actually need to understand how rocks respond to fatigue, to these very changing dynamic situations. And to assure the public of the safety of all of these technologies, we need to have good monitoring, good meaningful monitoring. So we need to understand the response of the rock mass to the heterogeneity to be able to design good monitoring systems. So how does heterogeneity matter? I'm probably preaching to the choir here at InterPore, but if we're thinking about injecting CO2 into a reservoir rock, and reservoir rocks in the subsurface are typically sandstones with grains of quartz feldspar with a pore space in between. That's if we're looking at a saline reservoir filled with saline water. If we're looking at a previously used hydrocarbon reservoir, we're thinking about water with potentially residual oil and gas. And when we inject CO2 into that formation, it fills the pores. If we have heterogeneities with finer scale pore throats, then as we inject the CO2, we may end up in a position where we have to push the CO2 through very narrow pores, in which case we want to know the capillary entry pressure of those heterogeneities. And the work to date in CO2 is almost entirely concentrated on heterogeneities that are related to the sedimentary structure of the rocks. Very little work to date been done on the structures and how geological structures such as fault zones can actually affect injectability of these of CO2, for instance. What do we know about faults at depth? Well, the hydrocarbon industry knows quite a lot. Faults can provide barriers to flow, which allow hydrocarbons to accumulate. Here are a couple of images that I took from the Fault Analysis Group website from University College Dublin. And this is a slice through a 3D seismic data volume showing seismic reflectors that have been coloured, that have been tied back to wells. And you can see the faults aren't terribly well imaged. The faults, in fact, are imaged by their absence. They're imaged by the fact that they've offset those seismic reflectors. On the right-hand side, we can see a 3D model that's been generated from one of these 3D seismic data cubes. And again, you can see the faults are imaged by their absence. There's no image of the fault rocks. They're just imaged where they've offset things. And this black line is the oil-water contact, where the buoyant oil sits higher up in the rocks, which are represented by the warmer colours, and the water is underneath that oil, lower down in the rocks, represented by the cooler colours. And you can see that those faults are providing traps for the oil against them. So there are a variety of ways in the oil and gas industry of forward modelling what those faults might look like, what their properties might be in the subsurface for a cross-fault flow. And by and large, they work fairly well, not under all conditions, but they're pretty good. But those same approaches don't predict a long fault flow very well. And if we're thinking about leakage to the surface, or if we're thinking about triggered seismicity, we really want to understand how those fluids may get into fault zones. They may leak up to the surface, or they may move to a part of a fault system that's closer to failure and trigger an earthquake. And in some places, faults can act as conduits and barriers at the same time in different parts, because they are inherently heterogeneous things. So let's have a look at some of these faults. On the top, we have an image of the slick rock sandstone in Utah that Carla took, and we can see typical reservoir sandstone, very high porosity. You can see cross-bedding here. This is the little laminae formed by the wind blowing across a desert when these things were deposited. And we can see these features here. These are deformation bands, these thin seams which cut through the rock. And here we can see a fault zone where those seams have become concentrated together and have offset this rock. If we zoom in and look at these structures, this is the same rock type now from a different part of the same field area, where we can see the host rock is this kind of yellowy colour, looks like beach sand. And we can see that cut by individual deformation bands and by clusters of deformation bands, forming this sort of tight zone of white rock. And that it's white for exactly the same reason as when you get brown sugar and crush it with a spoon, it turns into white sugar. And you can see in this example, we've had hydrocarbons infiltrating the rock, and those hydrocarbons have not been able to move through into those deformation bands. And that's because deformation bands form through localized grain rolling and fracturing. There's a nice little cartoon from Håkan Fossen. Here's a thin section image of one of these deformation bands showing that there's zones of grain crushing, grain fracturing, sometimes accompanied with dissolution and reprecipitation of the minerals in the grains. And what that does is it lowers the porosity, lowers the permeability, and increases the capillary entry pressure. But the question is, can we make predictions about this in the subsurface to help us understand how we treat these rocks in these future geological engineering scenarios? So what Carla did for her PhD, and I'm going to blatantly flag her 2 papers up here, and I'll repeat those at the end, but if you want to know the details of what she did, there's a huge amount of work gone into these 2 papers. She took 2 samples of the Navajo sandstone in Utah from a borehole that was drilled through a fault zone called the Big Hole Fault. Now, the Navajo sandstone is an excellent high-quality reservoir rock. It's used as an aquifer locally, but it's analogous to a lot of the reservoir rock in places like the North Sea oil and gas fields. Permeabilities of 100 to over 4,000 millidarcies. And we took a sample from 57 metres in the core and another one from 60 metres. And the first sample had effectively a single deformation band, though when you look in detail, you can actually see that these are 2 stepped deformation bands. and a sample from much closer to the fault zone itself, to the core of the fault, that is clusters of deformation bands. On the right-hand side, you can see images from the Strathclyde University micro-CT that is showing, the deformation bands are zones of higher density, higher attenuation within that image. And we can see that those deformation bands are tiny little faults that are offsetting the laminae within the rock along the bands themselves. So Carla conducted a set of experiments. So the first one was to look at single phase flow through a single deformation band. So she took water saturated samples and injected them with a radiotracer and looked at them under positron emission tomography to look at permeabilities. And then she conducted a set of two-phase flow experiments with a medical CT scanner, where she looked at, I'm only going to talk today about the nitrogen injection experiments into water saturated samples with one deformation band and clusters of bands. And these experiments were done at the lab in Stanford, where they have an outstanding lab for these kind of core flooding experiments. So I'll start off talking about the single phase flow. So what we're looking at now is a slice, or a sort of half cylinder slice through our sample. In each voxel is 0.23 on a side centimeters, and we have a plot of the normalized radio tracer concentration, and the tracer has been injected on the left hand side and being pushed through the sample towards the right hand side. Superimposed on the top of that is the location from micro-CT of the deformation bands, which are these diagonal lines, this pair of deformation bands, and the laminae, the natural bedding within the rock. And the deformation band porosities are between 0.07 and 0.15, and the laminae are similar to the highest porosity deformation bands. And again, this is calculated from the micro-CT data. So as the injection of this radio tracer proceeds, you can see it starting to invade the rock. You can see it pretty much ignores the laminae. It goes straight through. And as the experiment proceeds, you can see that the top of the sample is being invaded faster than the bottom of the sample. And if we keep proceeding through the experiment, we can see that the actual breakthrough of that radio tracer to the outlet occurs substantially earlier above the deformation band than it does below the deformation band. And the reason for that is that the pressure difference is the same across each of these two compartments, above and below the band. Note, there's no radio tracer at all within the band itself. That's not, the porosity has dropped down so much that there's no radio tracer making it inside the band. But the fact that you have effectively a sort of flaring of your channel below here means that the velocity decreases because the cross-sectional area is increasing. So you're actually getting a very different breakthrough time above the deformation band than below the deformation band. In the second experiment, where we have nitrogen injection into our water-saturated sandstone, we can see this is now a plot of porosity within the band, within our sample. The average core porosity is about 19%, but we can see it varies within the sample from very low to porosities in certain little points, really quite high, 30% or so. And we can see it varies along the deformation band in quite a complicated way. So we can see patches of very low porosity that move about depending on which slice you are within that deformation band. Within that sample. So yes, so we can see that we can image the bedding planes in terms of their porosity, and we can see that they're defined by stripes of higher and lower porosity in this slice, and we can see the variation of the deformation band porosity along its length. And as we can take slices through our sample and look at the slice average porosity, we can see the drop in porosity around those bedding planes, and an overall increase in porosity as we move from left to right in our sample. And we can use these data to calculate the overall permeability for the sample. And we can also use it to calculate permeability for the individual components of the sample, for the host rock and the deformation bands. So when we look at flowing through this, we conducted experiments with 5 flow rates, stepped up gradually, and normally you have to inject about 5 pore volumes between upping the flow rate but to reach steady state. And what Carla found was actually she needed to inject higher volumes. But for the single deformation band, we've got a map here, voxel size of 1.25 cubic millimeters, and we've got saturation, I should say nitrogen saturation, by the way, going from 0 to 1. And you can see that as we start to saturate this rock, we get very varying saturation, and we get much lower saturation underneath that deformation band, where the flow velocities were smaller in our single phase flow than we do above the deformation band. So we're getting a clear compartmentalization of the 2-phase flow as well as in the 1-phase flow. And at different flow rates, we see the same thing. We see the same patterns. We see this compartmentalization remains even at high flow rates. So although we are invading that lower compartment more when we have higher flow rates, we still see that that lower compartment has a lower overall saturation than our higher compartment. So next we're going to go and look at the clusters of deformation bands. And here we see a similar image. This is a porosity image now. And we can see the deformation bands of these zones of very low porosity, and they're chopping up that sample into isolated blocks of host rock material with the relatively high porosity. And at the top, we've got a more intense cluster of bands, sorry, on the left-hand side. On the right-hand side, we've got slightly lower intensity of bands and a higher average slice porosity. And with a bulk permeability of the entire sample of 0.18 millidarcies. So these are snapshots now at 47 minutes and 80 minutes of the full sample and the central slice. And this is nitrogen saturation again. And we can see that the nitrogen saturation is higher at the inlet side, but we still see areas where there's very low nitrogen saturation, and the nitrogen has kind of reached round into these high porosity compartments. We can look at the differential between those two times and look at where between 47 minutes and 80 minutes that nitrogen saturation is increased. We do the same thing for the snapshot between 80 and 160 minutes, and we see the downstream compartments starting to be invaded now. But interestingly, this large compartment here that looks completely blue at 80 minutes is only being half filled at 160 minutes. There's a single band here that's forming a barrier to invasion of that full compartment. And we can also see that, as I showed in the first set of experiments, the deformation bands have very variable porosity along their length. And we can see that it's the weakest, in inverted commas, parts of those deformation bands that are allowing that nitrogen to infiltrate into those compartments. It took 15 hours to reach steady state, but there were still some unsaturated compartments at the downstream end. Part of that is to do with the capillary end effect of the experiments, but part of those were quite far into the sample, so there were still places where the nitrogen had never reached. And these are the results for the slice average saturation at the end of each of the flow experiments. And you can see that this pattern remains, that there are compartments of low saturation even at very high flow rates. And so I think I'm running out of time slightly, so I'll go quicker. But this is showing you that the overall saturations at the end of the experiments are quite variable. And the pressure...
We have 10 minutes left.
Okay, I think, yeah, I have my conclusion slide just now. So, in short, the deformation bands are barriers to fluid flow. Now, we knew that already. We could see that from field observations. We could see that from data from the hydrocarbon industry. But this is probably one of the first set of experiments that's really pulled into the detail of this for single bands and clusters of bands. And what that means is that we get very variable flow rates within single phase flow. We get very variable saturations in multi-phase flow. And even though we have quite high pressures across our samples, we can, in the deformation band cluster samples, we can end up with very low saturations within part of that sample. So what does that mean for geological engineering? Well, because these things are barriers to flow, effectively they are reducing the overall volume available to put fluid into or drain fluid out of, if you're thinking about hydrocarbon reservoirs. So they reduce the overall volume of the rock that's available for storage, waste disposal, or so on. But counterintuitively, there's a group at Imperial College led by Sam Crever who has shown that these kinds of features in sedimentological scenarios can actually increase the residual trapping of CO2. The complexity makes it more likely that you leave some of that CO2 behind. So although these things may reduce your overall volume, they may make the reservoir a better place to trap waste. That being said, you need a careful consideration of your injection strategy, so you don't increase the pressure to the state where you actually rupture your fault zone itself, rather than the small deformation bands around the fault zone, or worse, rupture your top seal. Because we've observed breakthrough in individual bands, we can say it's not enough to just model this as a two-phase system with host rock with one set of values and deformation bands with another set of values. We need a stochastic approach to really capture the variability within those deformation bands that leads to that real complexity within these clusters of zones. So with that, I think I'll leave it there and encourage anyone interested to go and take a look at Carla's excellent papers. Thank you very much.
Sorry we cannot give you the applause you deserve after this wonderful talk. Thank you very much. That was very instructive. Please raise your hand, or I don't know what's the process for asking questions in this the Zoom setup that InterPore has given us. Can anyone from InterPore office explain how you ask questions?
Yeah. I think someone wants to ask questions, just raise his hand, and then you can mute him or her.
Okay,
Yeah.
Okay. But shouldn't I unmute him or her?
Unmute, because it's
yes,
automatically mute everyone.
Nobody has raised his hand yet, so I'm going to ask a question. Zoe, how do you feel that these results on this particular sample are generalizable to other fractured or fault zone containing materials?
So I think it's important to emphasize the difference between the sort of traditional conception of fractures and deformation bands. So rather, fractures are thought of as sort of openings where you'd have enhanced flow. Deformation bands are zones where you've crushed the grains and you've reduced the flow. But deformation bands are pretty ubiquitous in rocks that are relatively high porosity. And I've even seen them in pyroclastic flows that have come out of volcanoes. You can see deformation bands in. You can see them in gravel. Some fantastic work by Sean Lovelace showing deformation bands in these very large grain size rocks. So they're pretty ubiquitous. They are often they're tiny features, so they're not things that you can image on 3D seismic data. And there's a paper that Carla references in her second paper there by Scott Wilkins, where he works for Shell, and they had a reservoir where they were expecting a certain level of production, but they had much, much lower production than expected. And when they went back in and looked at the core, this field was full of deformation bands that they just hadn't imaged, they hadn't considered would be present. And when they factored that in, they found that could explain the lower production that they were getting. How you would do that in a field, if you were going from scratch and you had 3D seismic data, you wouldn't be able to image these things, but you might be able to take a kind of stochastic view on where they might be, understanding how those rocks were deformed and forecasting rather than predicting where those types of structure might be. be much better if you could have core, but core is expensive to collect.
Okay. Okay, thank you very much. I think we have a question from Andres Valdez.
Yes, thank you. Very nice talk. I was wondering if you can share some thoughts about mobility control. I mean, something like polymer or foam injection. I mean, it looks like the problem is that you have non-uniform breakthroughs. And I was wondering if you can make some comments on these mobility control techniques.
Sorry, I didn't hear the techniques that you were talking about.
Could be, for example, polymer injection, foam injection, or other things that might delay the breakthroughs and make them more uniform.
Okay. So how you might sort of engineer the rock mass to encourage a more uniform injection. I don't actually know anything about polymer or foam injection per se, but there have been some suggestions that there's a paper called something along the lines of why deformation bands don't matter, that argues that in certain geological scenarios, because these very thin zones are effectively stiffer than the rock that they sit within, that they're more brittle, and that if that rock is subject to the right kind of stress, you might be able to crack through those things. Certainly the deformation bands exposed at the surface in Utah, you can see those have cracked as they've come up, as they've been exhumed by geological processes. So, there's a possibility that you could look at affecting your kind of near wellbore permeability by stimulating the well, by fracking those deformation bands. It certainly wouldn't take the types of high pressures you need to frack a granite for hot, dry rock, but that may be one way of interfering with the near wellbore permeability field and get a more uniform breakthrough.
Any other questions? So Zoe, how do you think that one can do upscaling? If you have a core sample, I suppose it's of meter size, how can you upscale to the reservoir size your results?
So I'm a geologist, so upscaling is one of those things that how you practically do it, you'd have to speak to some other people in the team. But I would say that I think these effects you will see at a larger scale, and we see them. The image I showed of the rock that had the hydrocarbons percolated into it. So you can see that on the kind of, that's a hand specimen scale, but that's taken from a much larger outcrop where you've got one area of a fault zone that's maybe 100 meters long and 10 meters wide that has the hydrocarbon flow concentrated within it. So I think you see these compartments and these heterogeneities at a wide variety of scales. How you would practically go around upscaling that to make a forecast is beyond me. I'm sorry.
Thank you. Thank you. I see that Hadi, you had a question, but you raised your hand and now you are not raising your hand anymore. You are raising your hand again. Please ask your question.
Yes, hi. I didn't know my hands could be raised this way. Okay, so thanks very much for the presentation. I had a few questions, mainly about heterogeneity that you addressed. So if heterogeneity would help trapping gas in the subsurface, especially for the capillary heterogeneity that it would cause, wouldn't it be then a threat for a cyclic energy storage? Because you don't want to just permanently store the gas, you want to have it back again with the same purity as you have injected it before.
Absolutely, and I think that's not been well thought through or studied much.
Absolutely.
And I think there's probably something there about choosing optimal places for storage versus cycling.
Absolutely.
And simply thinking that and in a way we've seen this with CO2 reservoirs, haven't we? There's a lot of discussion around whether old oil and gas reservoirs are the best place to put stored CO2 or versus saline aquifers, because they will have had different stress histories. But certainly it's my feeling that energy storage, there needs to be a sort of separate set of criteria to decide where really good energy storage sites are. And I think you're exactly right that these kinds of feature are going to mean that you lose some of that material. The question that Stefan asked about the scaling, I mean, it may be much more useful to have energy storage in a sort of relatively small tank, as it were, rather than an infinitely big saline aquifer. So it could be possible that you used these smaller, you know, this compartmentalization to say, I'm going to be storing energy in this volume rather than the whole aquifer. But that really needs some attention to think about the kind of reservoir engineering implications of that.
Stefan, am I allowed to ask a second question? Do we have?
Of course, please.
Thanks
go
very
ahead.
much. Thanks a lot, Stefan. Good to see you, by the way, as well. So I wanted to also ask your comment about, Zoe, about cyclic experiments under CT. So if you would do cyclic injection of gas and into the core, you know, a sample, would that be kind of a straightforward thing compared to monotonely flooding as we typically do for nitrogen or CO2?
So again, the best people to ask would be Sally Benson's team at Stanford, because it's their lab that this work was done in. So in terms of the kind of experimental setup and experimental design, I would ask them. I think people have looked at cyclic experiments in terms of CCS. So there's this idea of push-pull experiments as a way of understanding the petrophysics of your near well bore.
Sorry for the interruption. I have to leave to animate SF MS09. So thank you very much. I leave you with the other panelists.
Zoe, I'll catch up later with you.
Okay.
So, but please continue, Zoe, with the audience, but I have to go.
Okay. I can't see people's hands raised, that's the only thing. So if you want to, just shout if you want to ask a question. But to carry on answering your question, Hadi, I'm working on a project at the moment with the University of Edinburgh where we're looking at the...
Catriona or?
Yes, Catriona,
okay.
Edelman and Chris McDermott. So we're looking at fatigue of rocks. We're actually looking at very high frequency fatigue. But they have a fantastic rig there that allows you to impose pressure variations, and when you look at high frequency fatigue, you actually reduce the breakdown pressure of the rock by 10, 20, even, well, they've got 30% reduction in pressure breakdown when they've used samples of PMMA rather than rock.
Well, thanks a lot. This is quite an exciting path forward to the community, as you just well said. So many things to study.
Great.
Thanks a lot for the nice presentation.
So if anybody else has questions, I can't see your hand raised, so you'll just have to speak them out loud, I think.
I think